Thank you so much, Michael Bush, for being here. I'm really excited. I'm personally very much looking forward to your talk, and I'm sure everyone else is as well. And so welcome to OTTER, everybody. Sorry for the late start. So Michael is going to be here talking to us about applications of matrix-valued Clark theory to differential operators. Take it away.
Okay. All right. Thank you for the introduction, and thanks everybody for coming. So this is work I've done in collaborations with my advisor, Connie Liao, and Rob Martin. And I should say kind of at the start that this work was partially funded by the National Science Foundation, as I'm contractually obligated to mention. So kind of the beginning of this talk, or the beginning of this work kind of starts with domains. And sort of orient us in terms of what I'm talking about when it comes to domains, here's sort of a toy model example of how sort of the domain impacts the properties of an operator, right? Because very often when thinking about an operator, we'll focus on the expression that defines it or the actions being done. But it can often be the case that the underlying set of objects on which you're performing those actions actually is really what's giving you the interesting properties. For example, take an expression that everyone's seen a bajillion times, the first derivative. If I define this sort of this finite dimensional vector space here, the derivative will have this representation. And then, which will have eigenvalues 0, 0. If I instead take the span of sine and cosine, the derivative will then have this action, and it'll have those eigenvalues. So in other words, we went from a single repeated eigenvalue to a conjugate pair. And so the punchline is that domains inform the spectral properties of an operator, even in, like I said, the sort of toy model finite dimensional example. Once you get into infinite dimensional things, as you might imagine, things get, the spectrum can get even more complicated, and the domain matters all that more. And so to kind of begin discussing that exact case, we're going to define a few domains associated with, or commonly associated with operators. So in particular, for a closed symmetric expression that's densely defined on an underlying Hilbert space H, we'll call the maximal domain of that expression, which we'll denote by dmax of t, to be the set of all functions that you can apply it to, right? Because note it's only densely defined, may not be defined in the whole space. And the and it has this property that the operator maps back into the Hilbert space. Now, and so you can view this sort of as being the largest subset of the Hilbert space on which T could define a self-adjoint operator. It's not guaranteed to, but it could, because in order to meet the definition of the adjoint for Hilbert space, you need to actually land back in the Hilbert space. Okay, so, and then we'll call the maximal operator associated with T, Tmax, which is just going to be T restricted to this domain, Dmax of T. Analogously, you can look at a minimal domain, which is, so again, I'm sort of talking heuristically here to avoid too much volume, too much notation at the beginning, but it's the intersection of all the domains on which T defines self-adjoint operator. So this is, in a sense, the smallest possible set that you could hope for your expression to define a self-adjoint operator on. And then, of course, that the associated operator is going to then be T-min, which is just T restricted to D-min of T. And one thing I'll note here is that T-min is the adjoint of Tmax. So those two are adjoints of each other. And so, as I've sort of stated, the minimal domain is going to be contained in any self-adjoint domain. And all the self-adjoint domains are going to be contained in the maximal domain, so there's some space between the two. And the exact quantification of that space comes in the form of what are known as defect spaces. So for the sort of standard assumptions, and when I say that throughout this talk, I mean closed, symmetric, densely defined, linear map. Its positive, negative defect spaces are given here, so they're going to be the kernel of the adjoint of T, essentially minus plus the identity matrix times I, or equivalently the perp of this range here. And then the dimensions of those spaces we're going to call the defect indices of T. And then kind of our first sort of result that's we're going to care about here is due to von Neumann, and that is that the maximal domain is precisely the minimal domain disjoint plus positive defect space, disjoint plus negative defect space. So you have, and so in particular, assuming that your defect indices are non-zero, you have a strict containment between the minimal and maximal domain. Okay. And to kind of give you a concrete example of what some of these things are, let's go back to the expression from the motivation slide, the first derivative, and let's look at the underlying Hilbert space, L2 of an interval symmetric about the origin. Then we have the following for our various domains. So the maximal domain is going to be the set of functions on which it makes sense to talk about a derivative, and where the derivative will map back into our underlying Hilbert space. Our minimal domain is going to be the functions in Dmax, because this is a subset of right, Dmax, with that go to 0 at the endpoints. And for kind of the folks in the audience that are into differential equations theory or into differential operators, the sort of general rule of thumb is that the minimal domain for differential operators will very often look like homogeneous boundary conditions, which is exactly what we have here, right? The endpoints going to 0. And our positive negative defect space are just the span of e to the x and e to the minus x respectively. In other words, our defect indices are 1, 1, right? They're both one-dimensional. And so in general, Dmax and Dmin are going to be infinite dimensional spaces, and D plus and D minus are, we're going to talk about the cases where they're finite dimensional, and most work is done in that regime. So, okay, so keyboard's being weird. Okay, so next we're going to talk about self-adjoint extensions, which are kind of really the crux of what I've been investigating recently. So, as I've alluded to earlier, an interesting question to ask is, given an expression and a particular domain, is that a self-adjoint operator, right? Does that define a self-adjoint operator, that pairing of expression and domain? And the set of all the domains on which that occurs are the set of all self-adjoint domains, and we'll call the operator restricted to such a domain a self-adjoint extension of T-min. Now you'll also hear this referred to as a self-adjoint restriction of T-max in some of the literature, but and they're equivalent, but it's just different authors like to use different wordings. And just again, kind of referencing what we've talked about already, remember the minimal domain is going to be a subset of any self-adjoint domain, which is going to be a subset of the maximal domain. Okay. All right, so now we're going to talk about how we parameterize self-adjoint extensions. So we have that the operator is self-adjoint, which is going to be relevant later when we talk about computing its spectrum. But how do we actually get at computing with these, how to actually get these restrictions? And there's a couple ways to do it. First, you can use a finite rank perturbation, the second is, if it's a differential expression, there's a theory about how boundary conditions and choosing boundary conditions will yield self-adjoint extensions. And then since both of these describe self-adjoint extensions, we're going to be able to form a correspondence between those two. Okay, so first up, self-adjoint extensions via finite rank perturbations. So for the purposes of this, we're going to assume that the defect indices of T are equal. That is, the positive and negative defect space are of the same dimension. Note that a priori that need not be true, but for the problems we're going to be considering, it will. We're going to assume it. And then we're going to let phi k be basis functions for our defect spaces. Then you have the following result, that if S is a self-adjoint extension of T min, its domain will have this form for some alpha that's an n by n unitary. So in other words, the defect indices, in this case it's going to be n, determines the size of the perturbation. So in other words, that example that we did with the first derivative, that had defect indices 1, 1. So in this case, alpha would be a 1 by 1 unitary, which is just a complex number on the unit circle in that case. And then you'd only have one defect function, so it would just be negative phi plus alpha phi minus. and you'd be looking at so you essentially only have one direction, if you will. That sort of is really what we're looking at, is how many sort of directions we're adding in order to get to a self-adjoint extension. Okay. Okay. And so now we're going to get into the other way of parameterizing self-adjoint extensions, which is via boundary conditions for differential equation. But before we can talk about boundary conditions, we need to set up the differential equation itself. So we're going to look at what are known as symmetric differential expressions. And the key thing to note is that these are differential equations that we're going to construct from a matrix of L1 log functions on some interval j, which could be infinite, but need not necessarily be. So this L1 log is important, right? If you're talking about an infinite domain versus a finite one, right? This can be different than just regular L1. So this matrix Q is going to determine our operator in the following way. So first, we construct what are known as quasi derivatives, which are essentially expressions that include the entries of Q, which again, since these are L1 log, these are functions in general, and derivatives of, and these primes are normal derivatives of lower order quasi derivatives. And then these spaces VR are essentially the spaces where we can compute these quasi derivatives, where the zeroth quasi derivative is the original function, much like with traditional derivatives, the zeroth derivative is just the original function, and V0 is just a set of complex valued measurable functions. And then through this process, we're going to ultimately care about the nth quasi derivative, and we're going to multiply that by I to the n, and that gives us our operator of interest. So that is kind of what you need to know from that. And so with this setup, now we can look at the self-adjoint extensions of that specific type of operator. So, and this is a theorem due to Glassman, Krein, and Naimark. Right, an operator is going to be a self-adjoint extension of a symmetric differential expression if and only if there exists, this should be an n, my apologies, n vectors such that, or n functions in the maximal domain such that they have the following three properties. First off, they have to be linearly independent modulo d min. And what that means, the phrase linearly independent modulo some subspace, is that it's just like the normal definition of linear independence, except you replace 0 with an element of d min. So in other words, if I have a linear combination of v1 through vn equal to an element of the minimal domain, those coefficients have to be identically 0. That's what it means to be linearly independent modulo a space. 2, this expression here, which is known as a Lagrange bracket, is going to evaluate to 0, and I define the Lagrange bracket down here. And the sort of motivation for this piece is if you imagine looking at the inner product of the nth derivative of f with g, just for two functions f and g, and you integrate by parts until you end up with f times the nth derivative of g, and you think about what those cross terms are, that's exactly the Lagrange bracket is what's going to pop out due to integration by parts. And sort of that. And so this equaling 0 is just kind of the definition of a self-adjointness, if you think about it that way. And lastly, the domain has the following definition. So a set of all functions that integrate against these n functions vk to be 0. Okay, so that's do Glassman, Krein, and Naimark. So in other words, what we're doing is we're taking functions that are in the maximal domain, they're beyond the minimal domain, and we're talking about self-adjoining extensions in terms of those functions. Whereas contrasting with the finite rank perturbation description is looking explicitly at basis functions for our defect spaces. So that's kind of how those two things differ. And before we move forward, just some quick notation. Because this is a matrix valued theory, so if I don't define some vector valued expressions, the slides are going to get really messy really quickly. So we're going to let f hat be the quasi derivatives from 0 to n minus 1 counting up. F check is going to be the quasi derivatives from n minus 1 to 0 counting down, all complex conjugate with negatives on the odd. what's the word I'm looking for? Negatives on the odd ones. And then using these notations, we can write the Lagrange bracket simply as the Rn dot product of those two vector value functions. Okay, so next up is going to be the promised self-adjoint extensions via boundary conditions result, which this is owed to Sun, Wang, and Zettel in 2009. And myself and my collaborators proved it in a slightly different way. Because funnily enough, there's been a couple of groups around the world working on this stuff, and they've all have slightly different versions of how to do it. And what ended up happening was we had when we were looking through the literature, we found a different group that had a subset of the result we needed. So we ended up generalizing what they did. And then like 2 weeks later, we found Sun, Wang, and Zettel had already done it, but we did it in a different way. So it was one of those things where we reinvented the wheel without realizing that it had been reinvented, or that it had been invented already, rather. So in addition to the usual assumptions, which is that everything that was on the handful of the slides setting up MQ and the stuff about T, we also need to assume that MQ is regular for this result to hold, and regular in the context of differential expressions just means that all your coefficients are L1. No, not L1 loc, like they were just to define the operator at all. They have to be truly L1 in order to have regularity. And if that holds, then you have a self-adjoint extension if and only if the following is true. So if you have these two matrices that are n by n, beta alpha and beta b, such that the rank of the augmented matrix, if you simply smush them together, is total n. They're equal to each other via this intertwining matrix C, which is just going to be -1, 1, -1, 1 on the off diagonal. Everything else 0 in that matrix, such that you have the following. So beta A f hat evaluated A plus beta B f hat evaluated B is 0. And recall these f hats are just our quasi derivatives counting up from 0 to n-1. And so this gives us now we have boundary conditions. So this looks completely like something from differential equations theory, contrasting the sort of maximal domain, minimal domain description and the defect space description from the other two ways of looking at boundary conditions. But this actually is related to the Glassman-Krein-Naimark result in the following way. So, and this is why I defined the check vector. So specifically, these two matrices are this check function, which remember that's computing quasi derivatives, run it backwards and alternate signs. So these two matrices, beta A and beta B, are constructed from those GKN functions in that way. And last but not least, kind of bring it all together for self-adjoint extensions. What is the connection between the finite rank perturbation description and the boundary condition description? And that is this expression here, where we have our defect functions, phi, k, right, phi j. We have our perturbation parameter alpha, which remember that's going to be an n by n matrix where n is the defect index of our operator. And these GKN functions that define the self-adjoint extension in terms of things that are in the maximal domain modulo the minimal domain. So that gives us the full picture of how all kind of three of these methods talk to each other, because now we're sort of evaluating at one endpoint and the other endpoint of the interval we care about. So we have boundary conditions in a sense. This is kind of tying all three together. This is what we get. Okay, so we have now sort of a translation between all the ways to talk about self-adjoint extensions, which brings us to the other half of the work, which is Clark theory. So before we delve too deeply into Clark theory, I'm going to just set up some notation, kind of further notation we're going to need. So we're going to let, what is this? It's a math cal U, n denotes set of n by n unitary matrices. We're going to let script S n of x denote the set of n by n contractions, which is going to be the unit ball of bounded analytic functions on a set x. Typically, x is going to either be the upper half plane or the unit disk, but a priori, this stuff could be done on other subsets of C, or even higher, or even C2, C3, etc. But we're just going to be focusing on C plus and D for this talk. And so, and the Cayley transform is going to be defined like this. So this is a Mobius, which is a fractional linear transform that's going to send the upper half plane to the unit disk. And if I have an inverse, that'll send the disk to the upper half plane. And then analogously, we can define the action Cayley transform in an operator like this, which is essentially just replacing the independent variable with the operator. And okay, so Clark theory. The way that all this stuff ties together is what Clark theory also allows us to do is compute measures that are tied to an analytic function. And what we're going to see in a second is that we're going to be able to take a differential expression and arrive at an analytic function that's going to encode its spectral information and put the two together, and you get from the expression to the spectrum via Clark theory. And so in order for this to be done, first we're going to talk about classical Clark theory, which will probably use theorems you're familiar with. So we're going to take an analytic self-map of the disk, and we're going to take a 1-by-1 unitary, which is just a complex number on the unit circle. Then the function u alpha, defined this way, the real part of alpha plus phi divided by alpha minus phi, is positive and harmonic. Therefore, by the Rees-Hurwitz theorem, there exists a positive measure, which we're going to denote mu to the phi alpha star power, such that u is the Poisson transform of mu, which is shown here. And so, we're going to call the collection of such measures the Clark measures of phi. So we start with an analytic function, we create a family of harmonic functions that induces a family of positive measures, and those are the Clark measures. And then there's an analogous result in the matrix case. This time we're going to look at an n by n contractive function, which is and an n by n unitary parameter alpha. Then we have a non-negative matrix valued harmonic function, through a similar construction. And then there's a matrix analog to the Rees-Hurwitz theorem that was not done by Rees and Hurwitz, but it's also not named after anyone. It's just kind of one of those things that you find it in like a 1920s Russian paper or something like that. It's one of those results. It's they did it in the scalar case, like I said, it was done by someone that they didn't think to name it for the matrix case. We just called it the matrix Hurwitz theorem. Gives us again now matrix valued measures, because we're working with matrix value functions that are again the Poisson transform, or that the Poisson transform of those measures gives us our harmonic matrix value function, and we're going to again call these the Clark measures. And now, because I know for me it's always kind of been a while since I've thought about measure theory in great detail, so I figure it's good to refresh ourselves about some of the basics of what it means to compare to, or the ways you can compare two measures. So, so we say that, so let XA be a measurable space where X is the underlying set, script A is the sigma algebra on X, and mu and nu are measures on that space. So we say that a measure is absolutely continuous with respect to another measure if, so mu is AC with respect to nu, if nu of A equals 0 implies mu of A equals 0 for all A in the sigma algebra. So in other words, this measure being 0 forces that measure to be 0. Then we say it's absolutely continuous with respect, mu is absolutely continuous with respect to nu. And furthermore, if a measure is absolutely continuous with respect to the Lebesgue measure, which I'm going to denote by M in this talk, then there exists an L1xm function, so a Lebesgue integrable function, which we're going to denote by d mu dm, such that integrating against our measure mu is the same as integrating against the Lebesgue measure with this weight d mu dm. And that looks like the chain rule, and so because it essentially is the chain rule for measures, and because of that, we call this quantity a derivative, specifically the Radon-Nikodym derivative of mu. And the other main way that two measures can be compared is a mutual singularity, which means essentially if there's a set in your sigma algebra such that, say mu is zero on every measurable subset of A, and nu is zero on every measurable subset of A complement, then those two are mutually singular with respect to each other. So in other words, they see completely different information. And sort of an easy example of this is the Lebesgue measure on a point mass. So say you have a point mass at 2, right? And I look at the set R minus 2. On the set R minus 2, that point mass at 2 sees absolutely nothing. And on the set 2, the Lebesgue measure sees nothing because the Lebesgue measure of a single thing is 0. And so we would say the Lebesgue measure is mutually singular with respect to point masses, which actually kind of dovetails nicely into the Big C Composition Theorem, which says if we have a Borel measure on a set X, and this is a technical need that essentially I believe in the proof of this, there's some topological considerations, which is why you see the word Borel making an appearance, measure on X with this property, finite total mass. Then it can be decomposed into two measures, the absolutely continuous part and a singular part, where, as you might guess, mu absolutely continuous is absolutely continuous with respect to the Lebesgue measure on X, and mutually singular is singular with the Lebesgue measure on X. And then furthermore, as it turns out, the point masses you sort of get for free that they're going to be singular with respect to the Lebesgue measure just by design. So very often the singular part is broken down into the pure point part, which is just the point masses, and everything else, which we call the singular continuous part. So in total, you get this decomposition. So the measure mu is equal to mu AC, where this is absolutely continuous with respect to the Lebesgue measure, mu SC, that is singular continuous, or that is singular with respect to Lebesgue measure and not point masses, and then you get the point masses. And yeah, so there's that decomposition. And sort of what we're going to do moving forward is look at the Lebesgue decomposition of Clark measures to get at the spectral information. Because remember, the Clark measures are spectral measures for a particular operator, which actually kind of brings us to our next point here. So we're going to, again, have a differential expression with all of the previous assumptions, the closed, symmetric, densely defined, regularity where appropriate. And we're again going to let phi denote bases for our defect spaces. So there's two functions that we're going to define. They're both in general matrix valued. In particular, they're going to be n by n, where n is the size of our defect spaces. You're going to have what's known as the analytic gram matrix, which is going to consist of inner products of our defect functions, and the characteristic function, which is due to Lifshitz, and it's going to be this Blaschke factor with a zi inverse, a z minus I. Okay, and so a theorem due to Alleman, Martin, and Ross, 2013, sort of connects these two. So the Clark measures of B are going to be the spectral measures of a family of extensions of T. So in other words, if I take an expression, compute its bases, compute the bases for its defect spaces, form this gram matrix, then form this characteristic function, which is also a matrix. It's sort of the product of these two matrices. And then I compute the Clark measures for this thing. That will give me spectral measures for T. And so just to kind of remind ourselves kind of really quickly just what a spectral measure is, right? If you think back to just vector spaces for a finite dimensional linear algebra, the spectral theorem says you get an eigenbasis if you have a self-adjoint operator and on a complex vector. On a real vector space, you get an eigenbasis. So in other words, you can decompose the whole space into eigenvectors of your operator. In the infinite dimensional case, the spectral theorem says that there exists a projection value measure such that you can integrate over the spectrum of the operator, and that's all you'll need to define the operator is essentially the integral over the spectrum of the operator. Which again is sort of the infinite dimensional analog of the discrete sum that you get from the decomposition you get from the finite dimensional spectral theorem. So that's where these sort of spectral measures tie into the spectrum specifically, is through that integration. So as promised, let's talk about the Lebesgue decomposition of Clark measures on T. So we're going to look at a function that is going to be an n by n contraction. So that's the unit ball of analytic functions on the disk. And the Radha-Nikodym derivative, so this is going to be for the AC part, is given by this expression here, where this delta is this symmetric term there. And one thing I'll point out is you can see that this is going to be non-negative definite, because this is just going to be a, where if you sort of look at this and you plug it in, you'll see that you're going to get a matrix times its adjoint, ultimately. So you'll have that. And then the pure point part is going to be governed by this limit here, which is going to be, and so kind of a feature I'll point out with this is that, note that, right, since we're talking about lambda on the unit circle, if z is going to lambda, right, z lambda bar is then going to 1. So this term will always be going to 0. So the only hope that you have that this limit is not 0 is if this matrix doesn't blow, is if this matrix goes to 0. Okay. And so those are kind of the 2 points. And the singular continuous part, I should say, is sort of, it's almost like the white whale of sort of spectral measures, in the sense that it's incredibly difficult to describe. And it's kind of one of those things where people have figured it out on case-by-case bases for specific operators. But generally speaking, when you're looking at formula for spectral measures, or you're going to see the AC part reported and the pure point part reported, but you're not going to necessarily have a clean expression for the singular continuous part. Okay. And so kind of the last sort of piece of housekeeping before we get to the examples is this conversion between the disk and the upper half plane. So previously we've talked about Clark measures on a disk. And as it turns out, essentially you want the boundary of your space to be where your spectrum lives, or the boundary of the subset of C you're looking at to be where your spectrum lives. So Clark measures on the disk are going to be a little bit more amenable to describing unitary extensions, right? Because that's where the spectrum unitaries live, on that unit circle. But if we want to look at self-adjoint extensions, that's going to be spectrum subset of the real line. So we're going to want the space of C we're working with, or the subset of C we're working with, to be the upper half plane, right? That's going to be our boundary. So that'll be the subset of C that has boundary R, is the upper half plane. In order to do that, we can use Cayley transforms, specifically the inverse Cayley transform, and we end up with this, this 1 over pi plus pi times 1 plus w squared is like a Jacobian that you might get from doing, sort of standard change of variables type computation yields this. Okay, so with that in mind, we can translate the results on the previous slide to talk about, now we have an n by n contraction with input in the upper half plane, and we have these 2 results. And so again, if you squint at this long enough, you can see that you're going to end up getting an operator times its adjoint. So you're going to get non-negative definite, or actually a positive definite, my apologies. And the pure point part is again governed by a limit that has a term guaranteed to go to 0. So ostensibly, the only way that you're going to have a non-zero register for a point is going to be, you have to have this thing go to 0 as well to create a L'Hopital's rule type situation. I should say L'Hopital's rule type, right, because this is a matrix and there's an inverse, so there's a bit more nuance to be had in the computations, but it's ostensibly a L'Hopital's rule type idea. Is the only way this can be non-zero if that part is going to be 0. Okay, so next up we have our applications to differential operators. So as I've said a couple times, right, the rank of the perturbation is going to be determined by the dimension of defect space, which we call the defect indices. And in particular, two examples of operators whose defect indices we can compute pretty quickly are going to be I to the n times the nth derivative on minus a to a, and negative 1 to the n times the 2nth derivative on 0 to infinity, both of which have defect indices n, n. So in other words, they're going to have an n by n unitary parameterizing its self-adjoint extensions. And note that these are in fact symmetric differential expressions with different underlying intervals, and this for a coefficient function matrix, which in this case is just going to be constants. But remember, a priori, this matrix could be full of functions that are 1 log j. I'm just kind of showing you a simple example here. And I say simple, then I flip to a slide that looks like this, right? So you have a, so our first example we're going to look at is going to be, we're going to be computing the AC part of the spectral measure for the self-adjoint extensions of the second derivative on the half line are going to have this form. So it's going to be essentially 4 times this expression in S, and then divided by this expression here. And the thing I want to kind of point out is if you look at this, this real part of root S actually is kind of one of the most important things going on here, because real part of root S has the unique, it has the property that it is going to be 0 for negative S, and because root of a negative number is purely imaginary, and we're going to get positive quantities for the for S greater than 0. And this is sort of as a known feature of the spectrum of the second derivative on the half line, is that you're only going to have spectrum in the positive real line, which this sort of confirms. And then yeah, so there's that. And then you can also similarly check that you're going to end up with something positive. If you look at all these terms, you'll get something positive here. And just a quick sketch of the proof. Kind of the way that all of these proofs are going to go are kind of start with some computation. So you compute the defect functions, which involves solving an eigenvalue problem. And then it looks like I messed up some tech there. Then you're going to normalize those, in particular with respect to plus or minus I. And then you're going to compute the Gram matrix, which is you're going to take this inner product against that. And then you're going to use the Gram matrix to compute the characteristic function. Now, since this is a rank 1 problem, the Gram matrix is just a scalar, right? It's a 1 by 1 matrix. Same with the characteristic matrix, it's a 1 by 1, since this is rank 1. But for a rank 2 example, you can, there's a lot going on, but so kind of the idea is that if you have a 2 by 2, that should be a 2, and you define these auxiliary matrices M and N, and this function kappa, then you'll end up with these for your matrix entries of your Clark measure, which, to reiterate, these are encoding the spectral information of the fourth derivative, is what these matrix entries are doing. And again, the way we arrive at them is going to be through starting with the defect functions. This time there's 2 of them because this is a rank 2 problem. Then we're going to, then you have to orthonormalize them. with respect to having plus or minus I in mind. Then you take an inner product a bunch of times to get the elements of the Gram matrix. And then you compute a characteristic function, and you're going to plug into the theorem, right, we have for spectral measures, and that's going to result in this here. And that can gets you the result on the previous slide, rather. Okay, so next up, we have I want to do an example of computing pure point spectrum. And so we have that for the first derivative. Now we're talking about a finite interval. The locations of the point masses are going to be given by this set here, where the inverse tangent is extended to include arctan of plus minus infinity. So in other words, it's this sort of periodic set. It's repeating right throughout all of R. And the way you get there is, again, it's kind of a similar thing before, and this tech missed way too many slashes for this talk. So again, this is now a rank 1 problem, so we're just going to have one defect function. It'll normalize like this. And then the analytic Gram matrix is going to be used as a scalar function that'll look like that. And then the characteristic function is going to be this ratio of signs. And then, as we sort of talked about before, this text is messed up. So the point masses are going to be when this expression is not equal to 0, which can only occur when the characteristic function tends to alpha, keeping in mind that alpha is unitary, so alpha times alpha star will give us the identity. And then if we apply this condition to our signs, we'll get that expression on the previous slide involving those tangents. If you use a bunch of your sort of angle addition formulas and angle subtraction formulas for your trig functions, you'll write that expression. And kind of an interesting side effect of this is, because we have a formula for the positioning of the point masses, we can actually track where they move as a function of the perturbation parameter. In particular, they actually are monotonically increasing with respect to the argument of the perturbation parameter, alpha. So if we set alpha equal to EVI theta and look at the derivative of this position with respect to theta, it's always greater than 0. So you have the eigenvalues, they all move together. Oh, and I don't know if I said this before, but right, the point masses of a spectral measure are going to be directly related to the eigenvalues of the operator. In fact, if you think about the operator spectral theorem, you'll see that they kind of, the point mass of spectral measure have to be occurring at the eigenvalues of the operator. And so these point masses, or these eigenvalues, they all move in the same direction with a speed that we can predict. So that's neat. And then to kind of finish this up, so I just showed you the location, but what is the actual weight of the measure, right? That's also important. And that's given by these 3 expressions, where the way you arrive at this is essentially, once you find where the point masses have to be, you just plug those into that formula and you compute a bunch and you'll arrive at these expressions, where you notice there's a point where you can divide by the imaginary part of alpha, which then means you have to kind of break the proof into 3 cases. If real part of alpha, or if the imaginary part of alpha is non-zero, this is true. And then for alpha equals 1, alpha equals minus 1, we have our separate kind of results. And an interesting feature to note here is that, right, this is a measure. So it may not look like it, but this will be non-negative always. In order to see that, what you can do is write the sign using the infinite product formula. And then, as it will turn out, due to the nature of this set P alpha, all but finitely many of those terms are going to be positive. And so then to figure out whether or not the measure is going to be to show that this is indeed a measure that's non-negative, you just have to look at those first k terms in the infinite product of the sign and figure out whether they're positive or negative and how many of them are positive or negative. And as it turns out, it will always be the case that that will pair with the parity of the imaginary part of alpha such that this whole thing is positive. And so, and to see this, you just kind of, like I said, just sort of keep going from where theorem 13 kind of left off to see that. So those are kind of the three examples I want to talk about. So to just wrap everything up, what have we talked about today? So given an expression, you can create operators with myriad spectral properties by pairing that expression with domains that are different. And then specifically, one type of domain that's interesting is a domain that induces a self-adjoint extension for that expression, because these are amenable to having their spectrum computed quite nicely. In particular, Clark theory can help us do that. And then if we add sort of the fact that if we work with differential expressions, then we get this ability to describe our self-adjoint extensions in terms of boundary conditions, which helps us interface right with other fields, because boundary conditions, for people that work in differential equations, they might not know what a finite rank perturbation is, but they sure as heck know what a boundary condition is. So we're able to sort of speak the language of multiple fields through these self-adjoint extensions. They let us kind of communicate between the two. And then, as I said a second ago, Clark theory can compute spectral measures for an entire family of self-adjoint extensions at once, which I didn't touch on before, but I'll kind of mention now, right? A priori, computing the spectrum of even one operator is a non-trivial task. But Clark theory can hit an entire, n by n unitary parameterized family of operators and get their spectral information out of it all at once. So that's nice there. And kind of sort of looking to the future, what are the ways this could go? Right, it only shows you a few applications to some, first derivative, second derivative, but clearly this can be done to much more complicated ordinary differential expressions. Another place this can go is for partial differential expressions, which is actually going to be interesting because for PDEs, the underlying spaces become much more complicated. You need to do things like work on Sobolev spaces rather than LP spaces or AC spaces. You need to work on Sobolev spaces. And also, I didn't mention this in this talk, but there's actually some distribution theory underlying some of this Clark theory. And for PDEs, the distributions are much more rich than in the ODE case, because the distribution is just typically just a Dirac delta for the ODE case. But there's some interesting distribution theory to be done, and there's interesting space, Sobolev space theory to be worked on, and integrating that into Clark theory. So that's an interesting direction. And also, kind of the thing I'll end on is saying that you can look at applications to operators on finite dimensional spaces, i.e. matrices. And this is a thing I sort of want to sort of just advertise to the operator theory community in general, because I feel like as analysts and as algebraists, right, we often have interest in the infinite dimensional case, in the spicier problems, right? But very often there is work to be done on finite dimensional vector spaces and problems that are underpinned by them. And in particular, you could look at, there's a lot of data science problems, right, that are all boiled down to manipulating matrices in various ways that operator theoretic tools could be useful for. And currently, no one's doing it. Most data science is going to be probability theory based, combinatorics based. Some of it you'll see, topology based, and then the bulk of it's going to be right just numerics. But there is ways to use quote unquote hardcore analysis to say something meaningful about these matrix systems, because ultimately these are just restrictions of problems that we may already be solving the infinite dimensional versions of. And that's sort of my mini TED talk within a talk about, that elusive word, phrase data science doesn't necessarily exclude analysts. I just want to kind of put that out there into the ether. And on that note, that's it. And I hopefully came in at under time. I'm a little bit over. So yeah, that's it.